In this lecture, we'll discuss hypothesis testing for a population variance, sigma squared, and for a population standard deviation, sigma. Recall that the population standard deviation is denoted sigma, this symbol right here, and it is always the square root of the variance, sigma squared. For example, if sigma squared, the population variance, is 16, then sigma, the population standard deviation, is 4. It's important to know when to use variances and standard deviations. Often it's more intuitive when we would use a mean or a proportion, but we don't always understand when variances and standard deviations can be useful. They can be useful in discussing the reliability of something. For instance, wait times for public transit. If a bus is 5 minutes early one day, 10 minutes late the next, 10 minutes early the next, and follows a pattern like that, it will have a high variance or high standard deviation. A high standard deviation means something is not reliable. In the same manner, the precision of a bathroom scale we'd like to be reliable. So if the standard deviation of what the bathroom scale is telling you is very high, that isn't very helpful if we're trying to monitor our weight. If it tells you you're 2 pounds heavier than you really are one day, 4 pounds lighter the next, and 2 pounds heavier the next, that would lead to a high standard deviation and low reliability. Additionally, when we discuss things related to volatility or consistency, we're also talking about the variance or standard deviation of the measurements. For instance, stock prices. We would like to invest in a stock that not only has a positive return, but also has a consistent return with a low standard deviation. If we're a sports fan, we enjoy it when our favorite players consistently perform well, when they get the same points per game every night, instead of going out and scoring 30 one night and then laying an egg the next. In general, if the variance and standard deviation are high, that implies high volatility or low levels of consistency. Note that volatility is the opposite of consistency and reliability, and all of these things we can talk about using standard deviations and variances. Typically, we don't like high standard deviations. High standard deviation means volatile. It means there's no consistency. Those are things we don't enjoy as human beings because we can't plan for the future. Let's take a look at an example. The typical variance for final exam scores of college students is 100. An ambitious professor wants to show that the variance in his class is significantly lower. Note here that a low variance would imply that all students are scoring about the same, indicating that everyone is learning at an equal pace. So while professors are interested in high grades, they're also interested in consistent grades. A sample of 41 students in his class take the exam and they record a sample variance of 75. Is there sufficient evidence at the 5% level of significance to suggest that his students have a lower variance than what is typical? Recall that typical is 100. As usual, we begin with our hypotheses. Since we're hypothesizing that the professor's class has a lower variance than the typical 100, our researcher's alternative hypothesis is that the variance sigma squared is less than 100. By default, the null hypothesis must be the opposite, that the variance is greater than or equal to 100. In our second step, we gather data from a random sample, or in this case from the problem, so that we can perform our hypothesis testing procedure. Note that the sample variance in this case is 75. We see that a sample of 41 students in his class recorded a sample variance of 75. That's where I got that number. A sample of 41 students leads to a sample size of 41. Our null hypothesis variance is 100. That's the variance the professor is trying to beat. We should put that right here, the null hypothesis comparison value. And we're testing at the 5% level of significance, so I choose my level of significance to be 5% or 0.05. Note, for this test, we will still need to worry about degrees of freedom, as we did with the t-tests. So the degrees of freedom follow the same formula, the sample size minus 1, or 40 in this case. Recall that in order to make our decision in step 4, we first have to calculate a test statistic and compare it to a critical value. Here we have the formulas for the test statistic and the critical value. The test statistic is calculated by taking the sample size minus 1, multiplying by the sample variance, and dividing by the null hypothesis comparison value. Here I've done the math, and I have a test statistic of 30. Check it on your own to make sure you're using the calculator correctly. The critical value here comes not from the t-table, where we've been finding a lot of our critical values, but from the chi-squared table, and we should get 26.509. Now I'll show you where that comes from. Here is a typical chi-squared distribution table. Notice there are 10 columns here that give us various types of critical values. Because we're performing at the 5% level of significance, we need to find a value that's in the extreme 5% tail of the distribution. Because we're doing a lower tailed test, a less than test, we need to find the area of the test in the left tail of the distribution. So we go to the middle of our table and we look at the left numbers. In this case, 95% refers to 95% of the distribution is above this value and 5% is below. So for one-tailed, lower-tailed tests, you will use one of these 5 numbers and you'll use the number that is the opposite of the level of significance. In other words, if your level of significance is 5%, you'll go to the 95% column. If your level of significance is 1%, you'll go to the 99% column. Since our level of significance is 5%, we're going to use the 95% column. We go down to the 40 row for 40 degrees of freedom, and we see the number 26.509. Make sure that you can find this number in your books too, and that you understand why I went to the 95% column and the 40 row. In step 4, we now make our decision about rejecting the null hypothesis. Recall that if the test statistic is more extreme than the critical value from step 3, then we reject the null hypothesis. In this case, more extreme would mean lower than the critical value. We see that the test statistic 30 is actually greater than the critical value, so we cannot reject the null hypothesis. Had the test statistic been less than 26.509, then we could have rejected the null hypothesis. So you may be asking to yourself, why lower? Why were we looking for a test statistic lower? Because the researcher's hypothesis, the alternative hypothesis, was that the variance would be lower than 100, that's why we were performing a lower-tailed test. Thus, in our step 5 interpretation, we say, because we were unable to reject the null hypothesis, that there is insufficient evidence at the 5% level of significance to claim that this professor's students have a lower variance on the exam than the typical class variance. Unfortunately, your calculators do not have a full hypothesis test for a one-sample variance test. Thus, you have to calculate the test statistic by hand on your own. Fortunately, that formula was not very difficult, just a simple multiplication and division. However, it'd be nice to be able to calculate a p-value with your calculators, and the good news is that you can. On your TI 83 or 84 calculators, press the second button and the VARS button, which will take you to your distributions. From there, select your chi-squared CDF. Be careful not to pick the PDF, so pick the second option, CDF. For this particular test, to find the p-value, you would input 0, 30, and 40 separated by commas into the chi-squared CDF function, and you would get a p-value of about 0.125, or 12.5%. Those numbers come from the 0 is always going to be a lower-tailed chi-squared number. X is the test statistic we calculated up in step 3, so that's why we put in 30. And here we put the degrees of freedom in the far right input, so we had 40 degrees of freedom. For any lower-tailed test, you'll go from 0 to your test statistic and then put in your degrees of freedom. Because your p-value, 12.5%, is greater than the 5% level of significance, again, that agrees with our first decision that we are unable to reject the null hypothesis. Let's do another example. A mutual fund is a collection of stocks. In a sample from the past 61 months, a particular mutual fund has an average monthly gain of 0.6% with a sample standard deviation of 0.5%. Is there sufficient evidence at the 1% level of significance to suggest that this fund has a true population standard deviation less than 1%? First off, notice in bold that there's a few things different about this problem besides the situation itself. Here I haven't given you a sample variance, but rather a sample standard deviation. And I'm giving you a test about standard deviations. I've also told you to test at the 1% level of significance. These are two changes important to this example. Also note that when we're talking about mutual funds, we would like to have a low standard deviation. So in this case, the investor knows that a 1% standard deviation from month to month is not good and wants to show that this particular stock performs better than that is, has a lower standard deviation. Our hypotheses for this problem are thus that we are hypothesizing or wishing to show that the standard deviation is less than 1%, or 0.01. I suggest when working with percents like this to use decimals. It's going to make your job easier. Our null hypothesis is then the opposite, that the standard deviation is truly equal to or perhaps greater than 1%. Notice what I've done off to the right. Originally, I made a statement about standard deviations, but we know that standard deviations are just variances square rooted. In other words, variances are just standard deviations squared. So if I square all four sides of my two hypotheses, I can say that the variance is greater than or equal to 0.01 squared in my null hypothesis, and the variance is less than 0.01 squared in my alternative hypothesis. This is an important step. If I give you information about the standard deviation, you should convert it to information about the population variance. It will make the test easier in the next few steps. As always in step 2, we gather the relevant data from the sample. Here we saw a sample standard deviation of 0.6%, which in decimal form is 0.006. So the sample variance would be the sample standard deviation squared, is 0.006 squared, which is 0.000036. Note that our null hypothesis value that we got in the step above is 0.0001. Our sample size came from the wording that we're looking for a sample from the past 61 months, and we're looking at a month-to-month standard deviation. So our sample size is 61 with 60 degrees of freedom. And I told you to test at the 1% level of significance. In step 3, if we choose to do our critical valued approach, then we need to first calculate a test statistic and then a critical value. Here our test statistic has the same formula as before. We take the sample size minus 1, also known as the degrees of freedom, multiply by the sample variance, and divide by the null hypothesis comparison variance. Now you see why we had to convert all of our standard deviations to variances, because we needed them as variances for this test statistic. If you do the math on this, you'll get 21.6, and again I urge you to try that on your own. The critical value from the book, which I'll show you in a moment, should be 37.485. To see where I got that figure, we know that we're doing a lower-tailed test, so we're going to be on the left side of our chi-square distribution. We want a 1% level of significance, so we're going to go to the 99% or 0.99 column, because that's the opposite of 1%. We go down, we find 60 degrees of freedom, and that's where I got my 37.485 figure. Now for our decision. If the test statistic is more extreme, again lower in this case than the critical value, then we reject the null hypothesis. Note here that our test statistic of 21.6 was lower than our critical value of 37.485, and so we must reject the null hypothesis. It is no longer plausible. From there, our interpretation is that there is sufficient evidence at the 1% level of significance to claim that this mutual fund's monthly standard deviation is less than 1%. That is, that this mutual fund is less volatile than a 1% standard deviation of returns on a monthly basis. On your TI 8384 calculator, if you'd like to calculate a p-value for this test, go to the same place we did before. Second button in VARS will get you to your distributions. Select the chi-squared CDF option. Enter 0 as your lower value, 21.6 as your test statistic, because that will find the probability of being lower than 21.6 all the way down to 0. And in your third input, enter your degrees of freedom. So again, in general, for a lower-tailed test, they'll go from 0, comma, test statistic, comma, degrees of freedom. Here the p-value on the calculator comes out to be about 1.779 e negative 6. So if you're unfamiliar with what this e negative 6 means, I'll explain it. E negative 6 means you multiply by 10 to the negative 6th. In other words, you divide by 1,000,000. An easier way to think about it is e negative 6 tells you to move the decimal point 6 places to the left, filling in empty slots with zeros. So I moved over once, twice, and all the way up to 6 times. I should get 0.5 zeros, 1779, so on and so forth. So I've rounded it to 0.5018. Obviously, this p-value is much less than our 1% level of significance, and again, we reject the null hypothesis because of a low p-value. This is the same decision that we made with the critical value. Either approach will always come to the same decision, whether it be reject or not reject the null hypothesis. So if you do it one way and then another way, and you get two different results from the critical valued approach and the p-valued approach, it would be good to check your work on both because one of them was probably done incorrectly.